let's now go through an analogous construction to set up the vector line integral. And so we can understand what integration of a vector field looks like and how can we understand what integrating this vector field over a curve is doing. So first, let's get some vector field in mind. Say f of x, y, z is, and we'll just call it like p of x, y, z, q of x, y, z, and r of x, y, z here, right? And so what the vector field is going to be here is, this won't look very good, but we have some vector field in 3 dimensions. Maybe doing something, right? Who knows? Based on these functions p, q, and r. Well, then we have some smooth curve, C. Let's get a smooth curve, C, parameterized by r of t, okay? And so maybe through here, we have some curve that behaves like this. We'll call this curve C. Remember, in blue is our vector field F. And to get an idea of what a vector line integral will tell us, it's helpful to consider, so let me also say here that the parameterization starts at time t equals a and ends at time t equals b. And so to get an idea of what a vector line integral is doing or what it's computing, let's think about work. So let's imagine this green dot here starting at r of a, right? Let's imagine this is some particle that wants to travel all the way to the other end of this curve, right? So r of b. And if it's in some vector field, you can think of this as force, right? Imagine this is like a force, or maybe a magnetic field or something, or a gravitational force field. Well, then for the particle to travel along this curve here, the difficulty that it's going to take to traverse this curve depends on if the vector field is like helping you or fighting you, right? And so if you're at a given point here along the curve where the vector field is, you could think of it like wind at your back almost. It's easier to run with the wind than it is to run against the wind, right? And so in certain spots, it's going to be easier to traverse this curve. In other spots, it's going to be more difficult. But all in all, there's going to be an amount of work that is required to move a particle from one spot on the curve to another, right? This is going to require some work. The work that F, so let's see how I want to word this. So let's pose a question. I like that better. What is the work done by F to move a particle along the curve C? Well, the answer is the vector line integral. The work, as we'll learn, is going to be the vector line integral of the vector field along this curve. And some notation here is we take the integral over the curve C, and this notation is f dot dr. Okay, so this is notation for the vector line integral. We will again construct a rigorous definition and then kind of a working definition for computing vector line integrals. And before we can start that, there's a few definitions that we would like to discuss. Notice, if I'm a particle, or if I have a particle along this curve, there are well, if I'm not completely at the mercy of the vector field or the gravitational field or whatever, and I can still move freely with altering difficulty, then I have freedom to where I want to go, right? I could traverse this curve in one direction, or I could turn around and traverse the curve, quote unquote, backwards in the other direction. And so this choice of direction that we are going to move is important, and this matters. This is called orientation of a curve. So definition, we say an orientation of C is a choice. So it's not canonical. It's a choice of direction along C. The direction we pick, so convention here, the chosen direction is positive orientation, or so is the positive orientation. The opposite direction, which we'll denote by negative C. So if you choose an orientation for a curve, well, then if you traverse the curve backwards, we'll say that's the curve negative C. But what this means is you flip the orientation, right? So the chosen direction is the positive orientation. The opposite direction is the negative orientation. And we usually indicate this with like plus and minus. And so if we chose, like say we have some curve here, we choose positive orientation to be to the right here, this is plus orientation. Well, then negative orientation is you traverse the curve backwards, right? And so again, this is not canonical. An orientation is a choice, right? It doesn't come with the curve. You have to pick it. Another definition that I want to give is a definition of a closed curve. A closed curve, C, is a curve such that, all right, ST for such that there exists, remember this backwards E means there exists, a parameterization R of T for A between, or T between A and B, such that R of A is equal to R of B, okay? And so you can see, imagine like we have a curve, so here's R of A. We've chosen an orientation, we traverse along this curve, and then it's closed if R of A is equal to R of B, right? And so it makes something that's like some shape resembling a circle, right? It's not, doesn't have to be a perfect circle. It can be very wiggly. And in fact, you could have self-intersection, right? This is a closed curve still here because I ended and stopped at the same point. When we talk about conservative vector fields, we'll get into like, when do we want self-intersections, when do we not, kind of stuff. In the meantime, we just care about closed curves. And in particular, let's just care about closed curves that don't self-intersect. Okay, so what do we have here? Let's actually construct the vector line integral. And so you can imagine, again, we have some curve C that's parameterized via R of T. And for T between A and B. And so once again, we're going to partition this interval AB into n subintervals, right? So we get like A is T0 less than or equal to T1 up to some Ti all the way up to Tn, which is B, right? This defines a partition of, so the ith interval is Ti minus 1 to Ti of length delta Ti. right? Or just delta t. And again, this defines a partition of our curve. So you'll remember, if we partition the time interval, well, then we can partition the curve at those specific times, right? And so we have, let's call the, we look at the parameterization at the t-ith time, and we'll call this point pi, right? And so we can partition c in intervals like pi minus 1 and pi. So we have like p0, p1, p2, all the way up to like pi minus 1 maybe, pi, and then all the way up to pn. And so this partitions our curve C. And once again, we need these sample points. Let's take these sample points. So we'll have some sample point in the time interval, say ti star, which is in the ith time interval. And this gives us a corresponding sample point pi star, which is equal to the, you just look at the parameterization of the curve at the time ti star. And we'll do this for all, remember this upside down A is for all I, ranging from 1 to n, okay? And so let's think about this now. We have pi minus 1, we have pi, and we have pi star here. And remember the length, so this is the ci curve, or subcurve here. So this is ci. And remember, what's the length of ci? Well, this arc length here we call delta si, right? And so we'll stick to that notation. Well, if pi minus 1 and pi are sufficiently close, so let's say pi minus 1 and pi sufficiently close, we can assume this sufficiently close, because if you have a given partition and these 2 points aren't close enough, well, take a partition of that partition, right? And then it's much more fine. And you can keep doing that until your pi and pi minus 1 are sufficiently close. Well, this means then the length here is going to be approximately linear. But more importantly, what this means is if we think about a particle traveling along this curve, let's give it this orientation here, right? Just without loss of generality, we've oriented this curve to the right. As we travel along this, we know the velocity vector corresponding to the particle moving is tangent to its path, right? And so we have some tangent vector. Moreover, we can think of the unit tangent vector. So we'll think of the unit tangent vector t pi star. This is the unit tangent vector at the point pi star, right? And why do we care? Well, this gives us the direction of travel. If pi minus 1 and pi are close enough, then this direction, the direction in which the particle is moving at pi star, is basically the direction, I mean, approximately the same direction as a tangent vector. So what this means is particle moves approximately in the direction of the tangent vector, the unit tangent vector at this point. And so now let's calculate the work done to move a particle from pi minus 1 to pi. The work done over ci. Well, we know what this is, right? It's force. Work is force times distance. So what's the force? Well, the force is going to be whatever the vector field is doing at this point, right? Remember, we have a vector field here that's representing our force field. And so the force is this vector field. And then what's the distance? Well, the distance, the total distance, is the change it's the arc length, right? The total distance is this here, this length of the curve, which is delta SI, but we also need to indicate what direction we're traveling in. So this is times, and again, if these are sufficiently small, this is the direction t of pi star. It's the tangent vector at this point. And so therefore, the total work, you could take the sum, right? So the sum would be going from I equals 1 to n of f of pi star times t of pi star delta si, right? This would be what the total work would be, because you would do this construction here for every single I, right? For all I ranging from 1 to n, this would give you the work along the whole curve. And so with this sum here, this allows us, taking the limit as n goes to infinity, we get a definition for the vector line integral. The vector line integral of vector field f along an oriented smooth curve C is given by, well, we say this is, here's some more notation. We'll write this as f dot t ds, and this is the limit as n goes to infinity of the total work done. I equals 1 to n, f of pi star t of pi star delta si. And notice this is dot product, because these are vector. These are vectors, right? We're looking at a vector field and then the tangent vector field here. So this, it's important that we know, we think of this as dot product. Now that we're in the realm of vectors. And so again, for notation here, what we can say for, let's get some more notation. We write f dot dr is the same thing as f, the integral over the curve, the vector line integral over the curve C, and we write f dot dr in the integram. This is the same thing as f dot t ds, right? We're just making this substitution. This will become a little more clear why we use this notation later. But it's pretty intuitive when you actually construct the integral from the ground up. It's intuitive that we write it as the vector field dot the tangent vector field, right? Because in the construction, that's what we get. We get f dot t. And so we'll see why, in a while, we'll see why we use this notation. And so here's a theorem for calculating vector line integrals. We say the vector line integral over the curve C of f dot dr is equal to the integral from a to b of f of r of t times r prime of t dt. And so here's this theorem. And where did it come from, right? Where in the world did we get this formula? Well, let's recall what, so here's a quick proof. Let's recall what t prime of t is actually doing, right? Remember the tangent, the unit tangent vectors are the derivative, because the derivative gives you something tangent to your position. And then to get a unit, we divide by the magnitude. Right? And so using this, and then also, if you'll think way back to the previous video, in our definition or in this theorem for calculating the scalar line integral, there's a subtle equality here that can be used to our advantage. And it's that ds is equal to the magnitude of r prime of t times dt, right? Because here is f and here is f. So the only thing that's different here is ds and r prime of t magnitude dt, which means there's a subtle deduction that those are the same. Therefore, we may write that, so we have this expression for the, not prime, sorry, this is not prime. That would be a normal vector. I don't want you, all right. This is just t of t, right? And we also have that ds is equal to the magnitude of r prime of t dt. And let's use both of these things and plug them in to this expression here. So what we have is that the integral of cf dot dr, well, using our notation, this is the integral of f dot t ds. Well, integral f t is then r prime of t over, sorry, this should be a capital F, right? Because we're looking at a vector field, my apologies. We have r prime of t over the magnitude, because this is our representation of the tangent vectors, and then times ds, right? And ds was magnitude of r prime of t dt, which is the integral from a to b of f of r of t, right? Just writing that more explicitly. And then we get cancellation of the magnitudes. And so this is times r prime of t dot product, right? Not times. These are vectors. These are vector fields. So dot product r prime of t dt. And this is the proof for this theorem here. So we can use this. So where C is, again, an oriented, smooth curve with parameterization r of t for t between a and b. And so this is a very useful theorem, just as we saw for scalar line integrals as well. We get one for vector line integrals. And remember, to reiterate, this was supposed to be a capital F all along. I made a small typo there. Because we haven't been working with the scalar lowercase f, right? So here's a quick example. So let's find the vector line integral over some curve C of f dot dr, where C is parameterized by r of t equals cosine t sine t for t between 0 and pi. Okay, so what do we have? Well, integral c f dot dr. And I should tell you what the vector field is, right? That might help. And the vector field is given by this rotational vector field that we examined in the previous video. Okay, so what do we have to calculate here? Well, we need a and b. Well, we know what a and b are, right? That's the easy part. Those are the bounds. Those are the bounds on our t for our parameterization. So we know that goes from 0 to pi. Well, then we need f of r of t dot r prime of t dt, right? That's exactly what this formula from the theorem states. So again, I like to calculate these in pieces. Well, what's f of r of t? That means we just plug our parameterization into the function, right? So y is sine of t, and so the f of r of t, the x component is going to be negative sine of t, and then the x component is cosine of t, so the y component of f of r of t is going to be cosine t, right? This is our f of r of t. And then what is r prime of t? R prime of t, well, we look at r of t and take the derivative. So the derivative is negative sine of t cosine of t. Cool. And so now let's use these, plug them into the formula, and see what the integral simplifies to. This is equal to the integral from 0 to pi of negative sine t cosine t dot product negative sine t cosine t dt. Okay, so now we actually take the dot product here. And so we'll get negative sine t times negative sine t. So that's positive sine squared t plus cosine squared t dt, which is integral from 0 to pi dt, which is pi. And so this would be the work done for a particle to move along this curve via the given vector field negative y, x. Okay, so there's a nice example of how to use the formula. And next, let's even more notation, right? And this is me making it clear why we use the integral cf dot dr. Well, if we think of f as our standard vector field PQR, where PQ and R are all functions of however many variables you have. And what would dr be, right? Well, dr would be dx, dy, dz. It's the differential expressed as a vector, hence the vector over this r here, because it's like the differential, but we're expressing it as a vector. And so that means sometimes the notation may look like this. So we have the integral over the curve C of P dx plus Q dy plus R dz. But these are the same, right? And so you integrate in the same way, right? These are still like components of a vector, and you have to do, it's just like now the dot product is already expressed, right? Because I've actually taken f dot dr. And if I took f dot dr, I'd get p dx plus q dy plus r dz. That's exactly what this is here. And so nothing's changed, right? It just looks different. And so that's one thing I would like to state. Now, there are some properties of vector fields or vector line integrals that are worth mentioning. The first one is that the vector line integral of the sum of, so say you have like some vector field that's given by the sum of two other vector fields, dot dr. Well, this is the same as take the vector line integral over the first plus the vector line integral over the second, and that should be a g, sorry, not a very good g. Okay, the second one is constants behave how you would like them to. So if you have some scalar k times f dot dr, well then this is the same as, you can pull the k out front and then integrate the vector line integral normally. The third one, which is really important, is if you take the vector line integral along a curve with negative orientation, you can calculate this vector line integral by taking negative the vector line integral along the positive orientation. And so this one's really important, right? Because sometimes working with negative orientation can get a little ugly. Or in general, maybe it's positive based on your choice. In general, sometimes working with one orientation can get a little not fun, right? And so this property is very nice. It says, well, it doesn't matter. You just have to pick up a negative when you flip the orientation. The last property I want to talk about is if you have, so let's say C is piecewise smooth, meaning, you know, there could be areas where there's like sharp turns, but if you break it up into pieces, like each piece is a smooth curve here. And so let's say C is some piecewise smooth curve, and we break it up so it's like C is C1 plus C2 plus Cn, where all the C1s through Cn are smooth, right? So this is a little bit, this gives us a way of looking at a little more general curves here, right? And what it is that the vector line integral of some vector field over this curve, over this piecewise smooth curve, is the same as taking the sum of the vector line integrals over every piece, right? And so you can avoid difficulty of these sharp turns by passing the integral to the integral over each piece. Okay, and cool. So there's the definition of vector line integrals, the rigorous definition, the working definition, an example, some properties, and lastly, I want to spend maybe 5 minutes on applications of line integrals. So the textbook, the OpenStax textbook, has examples of all of these applications. I would strongly recommend you to go, after I give the list of applications, I would strongly recommend that you go take a look at these examples, because some of them I know for sure work, and calculating work and flux will be on the homework. And so it would be a very good thing to go over these examples on your own to get a good idea of these applications, because it's still just calculating line integrals, right? But the physical setups are quite interesting. And so the first application is calculating the mass of a wire. Okay, so mass per unit, say mass per unit length. Well, this is a continuous function, right? This is a continuous function. Mass per unit length is what we think of density, right? Because it's weight, it's mass per area, which is density, right? And so we write this like rho of XYZ, right? And so this is a continuous function. Well, then the mass of a wire, so if you have some wire C, then the mass of this wire is simply the scalar line integral over the wire of the scalar function you use is the density function, ds. And so you can calculate mass of a wire if you know its density. And you'll have to parameterize the curve, of course, right? What's another application? Is calculating work. Right? We've seen this here. So it's the work to move. So it's the work required to move a particle along C in force field F. And we know that this work is the vector line integral F dot dr. So again, you have to parameterize your curve. You have to know what your you have to know a representation of your vector field, and then you can calculate work. The last application I want to talk about is flux. And so let's give a definition. So what is flux, first off? Maybe before I just start throwing a definition out, let's understand intuitively what flux is. Let's imagine this is like a really thin membrane, some like permeable curve where maybe like part of a cell or something where water could pass through it. And, you know, based on a lot of factors, water could be coming through really quickly at one spot and then like really slowly, right? And maybe somewhere not even at all. Maybe there's some obstruction and it's like not even going through at all or something. Well, calculating the tendency of this water to go through the membrane, this is an idea of flux, right? It's kind of how much is this membrane allowing in and out of a given region. And so this is the idea of flux. So, and how do we calculate flux? The flux of F, right? Because this would be some vector field F. The flux of F across C is, and let's write this here. So let's remember the vector line integral over the curve C of F dot capital N ds. And let's remember what capital N is. These are unit normal vectors. So this is integral over the curve C F dot N, where N are normal vectors, and then you divide by the magnitude to get unit normal vectors, right? ds, and so this notation is kind of silly here, but we remember what ds is, and this simplifies to integral over the curve of f of r of t times n of t dt, right? Using our same expression for ds that we did previously, but now with n of t instead of r of t. And so we can use this to calculate the flux of F cross C. Okay, and again, I would strongly recommend reading those examples over these three these three applications of line integrals, because they will show up on the homework and we will talk about them in recitation, and they could possibly be on the final. So, but aside from all that, I think it's very interesting. And if you think it's very interesting, then I would definitely recommend checking it out. Okay, so this wraps up our talk on line integrals. We've seen some good constructions and good examples. And now we'll be discussing in more detail conservative vector fields. So that's where we'll be going next.